what is it that we're trying to prove? What does this even say? Okay, let's take some concrete numbers for n. What does it mean to write down the sum like that? What does it mean? So n, does it even, okay. So here's one of those expressions for a given n. Let's suppose n is 3, 3. 2 plus 2 squared, okay, plus 2 to the third is the next power, so 3. So I have n plus 1 terms in the sum, 3 plus 1 terms, 1, 2, 3, 4, 3 plus 1 terms. And that's going to be the sum of those powers of 2, of all powers of 2, beginning from the 0th power up to the nth power of 2. It's going to be the next power of 2. What do I mean by the next? The 4th power in this case. N was 3. This is n plus first power of 2 minus 1. Okay, so that makes sense. So for example, on the left-hand side, you have 8, 4, 2, and 1, and that's going to be 15. It sums up to 15. So this is 16 minus 1 on the right-hand side, and so on. On the left-hand side, you have 1 plus 2 plus 4 plus 8. That sums up to 15. Okay, when n is, we probably don't need to write down another example, but let's say when n is, let's write 2 as the 0th power. Plus 2 to the second, plus 2 to the third, plus 2 to the fourth is going to be 2 to the fifth. Now, the next power of 2, minus 1. So you probably have thought of this. You know why this is true. You know what's happening here. Okay, these are, maybe you thought of this in the context of base 2 notation, or simply you thought about powers of 2 in some other context. This works. Now let's prove that this indeed is the case. Okay. So what is the, now back to our discussion. So how do we prove statements like this using induction? So we have an infinite number of statements, right? So these are just 2 examples of an infinite set of statements that we need to prove. All these statements are indexed by n. So P of n is, we call this a proposition. You can refer to it as a predicate or a propositional function. So what is P of n? So it's important to write down in words correctly what P of n is. So what is P of n? So let's express it in words, in a natural language, like English, in a human language. I mean.
It's a sum of the powers of 2 to n.
So, yeah.
Is that what you're asking?
Yes, that's what I asked. But is this P of n sum of the powers of? So let's have a full sentence, like an English sentence that we can call a proposition. So sum of the powers of 2. If an English teacher were to stop by, they would nitpick. They'd say it's not an English sentence. They'll say something along those lines to annoy people. They will say it's a phrase, it's not a sentence, or something like that. An English sentence needs a subject and the predicate, blah, blah, blah. Whereas P of n is a proposition. It's a propositional function. Okay, so what would be the proposition itself? What is it that I'm trying to prove? It is super important to have these notions very clear in your mind before you attempt to prove. Otherwise, what are we doing, right? So what is P of n?
I would say P of n is it would say the sum of 2 to the n from 0 to n is equal to 2 to the n plus 1 minus 1 for all like n greater than 1.
So the predicate is exactly what you said. The predicate is that equality is true or false. So that is already a proposition, a logical proposition. It says this sentence here is this equality for any given n. Is it true or is it false? That's what we're evaluating. So P of n is the statement that the sum of the first n powers of 2 is going to be the next power of 2 minus 1, the n plus first power of 2 minus 1. That's in words. We write this down this way. Okay, so plus 2 to the n, dangerous ... We'll talk about dangerous ... later today. Is the next power of 2 minus 1. That's a proposition. For a given n, that's a concrete proposition. N changes, I have a different proposition. And I want to prove that all of these propositions, of which I have 1 for each n, is going to be true. Okay, we want to show that P of n, this proposition that I've just written down, is true for all n. Okay, makes sense to everyone, right? Okay, now we're getting to what you've explained to us. We have certain steps that we need to follow to carry out a proof by induction, meaning to carry out the proof that all of these propositions, an infinite number of propositions, all of them are true. For us to prove this, we can follow the template of mathematical proof by mathematical induction. Okay, so we have a basis step. So what does this equality mean when n is 0? So it looks like we're starting at n equals 0. What does it mean? So what
2 to the 0 power
yeah,
should equal.
Yes. So let's write it down explicitly. Yeah. Yes, go ahead. Yeah.
Oh, okay, go ahead. Okay, 2 to the 0 power
Mhm.
should equal 2 to the first power minus 1. 2 to the 0 plus
Yeah.
1 minus 1.
That's exactly right. Okay, so let me read
Which
that.
is true.
Yes, that's exactly. So P, just so that everybody sees, P0 is the statement. The statement. Okay, so notice the P of 0 is a statement. Let me put it in quotation marks. Nobody puts this in quotation marks, but I will. That 1, which is 2 to the 0th power. So let me, just to be even more explicit, don't have to write this, but I will. 2 to the 0th. This is 2 to the 1st. Says, okay, so these are ends there. Okay, so what we have is 2 to the 0th is 2 to the 0 plus 1. So all I did is I just plugged in 0, as you told me, for n here in this proposition. Minus 1. Okay, that's the statement. Now the question is that statement true? And the answer, but P of n is true, of course, because 2 to the 0 is 2 to the 0 plus 1 minus 1 is 2 to the 1 minus 1 is 2 minus 1 is 1. 2 to the 0th is 1. So because 1 equals to 1, okay, this is a very lengthy way. So you just, everybody saw this immediately, but I'm just writing down just to be very, very explicit. Okay, so that's true. Everybody's on the same page with this, right? So 1 is 1, and we've just verified that one of those infinite statements, if P of n's is P of 0, is true. Now we have an inductive step. What do we prove here?
We're going to assume that for some k, which is greater or equal to 0, the proposition holds. So P of k equals 1 plus 2 plus 2 to the k power equals to 2 to the k plus 1 minus 1.
Holds. Okay, so that, let's go gray here. So P of k is, we know what it is. So 2 plus 0 plus 2 plus 1 plus blah, blah, blah. 2 plus k is 2k plus 1 minus 1. What is pk plus 1? We want, assume. This is assume. Show. We need to show that P of k plus 1 holds. So let's write down P of k plus 1 is, okay, so 2 of 0 plus 2 of 1 plus blah, 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 2k plus 2k plus 1. This is what we need to show. So that in this step equals, what did you tell us?
2k plus 2
2k
minus 1.
Plus 1 minus 1. This is what we need to show, right? Just why did I write it this way? I just plugged in instead of k plus 1 here in my general expression. I plug for n, I plugged in k plus 1, so I have k plus 1 plus 1 here. That's what I wrote down here. Okay, so that's what we need to show. Okay, but so I'm writing down the expression for pk plus 1. K plus 1, and I want to show that this somehow, this is going to be that. This is where I'm headed towards. Okay, so this is my clean write-up is here. Okay, so what should I say? I will say that because of the inductive hypothesis, the blue piece here is going to be 2 to the k plus 1 minus 1. That's the blue piece. And then I have this term, 2 to the k plus 1, right? Everybody agree? Just by the inductive hypothesis. So by the inductive hypothesis, that has to be true. But then, of course, that is true because we get to assume P of k. So because P of k was true, this is the same as 2 times 2k plus 1 minus 1 by algebra. By algebra, right? Okay, so by algebra. And that, continued here, is equal to 2k plus 1 minus 1 by algebra. Again, right? So that's exactly what we wanted to prove. Okay, this verifies the inductive step, the inductive step. Any questions? I have one more thing to say, is that because I've verified the basis step, and because I've verified the inductive step, I can apply the principle of mathematical induction that tells me that my P of n has to be true for every n. And that's it. Then I say that I'm done with the proof, QED, and that's it. Does this make sense? So this was just a review from last time. Okay. Okay, so we'll do more examples. Let's do one more example. I think that people asked about inequalities and so on. So let's do an example where you don't have to start your induction at 0 or at 1, like our previous examples. Let's do this one. Now you help me. So this inequality here, I want to prove that 2 to the n is at most n factorial. Now, if n is 1, then 2 to the 1 is not 1 less than 1 factorial.
Doing anything to stop it? The governor's not doing anything? Sorry.
Okay, so if n is 2, then 2 to the 2 is not less than 2 factorial, is it? If n is 3, 2 to the 3 is not less. Well, what is 2 factorial? It's 2. Here I have 4. Okay, here I have 1. Here I have 2. 2 to the third is 8. 3 factorial is 6. Right? 1 times 2 times 3. But when n is 4, okay, 2 to the fourth, which is 16, is going to be 4 factorial, smaller than 4 factorial, which is 24, because 4 factorial is 3 factorial times 4. So 1 times 2 times 3 times 4, that's going to be 24. So that checks out. Now, what this problem is asking us to prove is that this pattern continues. Okay, it didn't hold for n1, 2, 3, but when you hit n4 and 4 and onward, this inequality will hold. So you may say this is slightly different than in our previous examples, we were always proving that something equaled something else. But I'll say no, it's exactly the same as the ones before, because we're proving a proposition and an infinite number of propositions in a few minutes. How? We're following the principle of math induction, which tells us how to do just that. Now, the proposition here, this proof is by induction. So what's the most important thing? Let Pn be what proposition? Be the proposition that, and now I'm going to put quotation marks. So what's P of n? It's some logical statement, which is either true or false, which is indexed by n. That's all the predicate is in the context of inductive proofs. It is a proposition that depends on n. So what's the proposition?
That 2 of n is less than n factorial.
Yeah, exactly. It's very simple in these examples. 2 to the n is less than n factorial. That's the proposition. End of quotation marks. Let's make these quotation marks. like that. I don't know if that's any clearer, but okay. So now what we want to prove is that all of these PNs are true, starting from 4 and upward. Okay. We want to show, again, show that all P of n's for n greater than equal 4 are true. Okay. Usually you'd write this down. I want to show that P of n is true for all n when n is greater than 4. But let's write it down this way. Why not? So now the proof is, we just said that the proof was going to be by induction. So we write down the base case. Okay. What is the base case?
P of k equals 4, okay?
Yeah.
So P of 4 will be 2 to the 4th power less than 4 factorial.
Exactly. Is true, which we've just verified is true. The base case is done. Inductive step. The inductive step is what?
I'm going to assume that for some k, which is greater than or equal to 4, that P of k is true. And we want to prove the implication that P of k plus 1 is true.
For any k that's greater than or equal to 4, assume that P of k is true. Then I'm writing down pk of plus 1. Let's skip the Simpsons cloud now. What is it that am I proving? Exactly what you just told us. 2 to the k plus 1. Okay, let's write down Simpsons cloud. Okay, so let's write down. So here's going to be, I want to prove that 2 to the k plus 1 is going to be less than k plus 1 factorial. That's what I want to show. I don't know if it's true, but here, apparently it is true because 2 to the k plus 1, now I want to get to use, so what should I do? I want to use the inductive hypothesis somewhere. Okay, let me write it down step by step. 2 to the k plus first power is going to be 2 times 2 times k. That's by algebra. This, let's make pieces blue. 2 times 2 to the k is less than or equal than 2 times k factorial. This guy, okay, maybe I shouldn't underline, it's already in different color, by the inductive hypothesis. Okay. As an aside, we can erase, this is from last lecture. So let me use some space here. Now, any ideas? So this is what we want to prove is this here. Okay. Because k is greater than or equal to 4, 2 is going to be always smaller than k plus 1. Okay. So let's use yet another color. So this is going to be less than or equal, because of this, k plus 1, because 2 is smaller than k plus 1. I mean, k is 4 and bigger. So 2 is smaller than k plus 1 times k factorial, which is, by definition, k plus 1 factorial. That's it. That's the entire argument. Okay. So 2 to the k plus first, which is shown, has to be at most k plus 1 factorial. Right? Everybody agrees, right? That must be the case. So we've just shown the basis step. We've just demonstrated that the inductive step must hold. We assume that P of k is true, then P of k plus 1 must hold. Therefore, P of n is true for every n. This concludes the proof. That's it. Follow the template. Nothing creative here, except I had to do some work, but just blindly followed the template. What is important is to clearly, in words, say what P of n is and have it clear in your mind. The rest just falls into place, like little puzzle pieces.
I have a question.
Yeah.
Is it possible to say that we want to prove something which is true, and that is that 2k plus 1 is less than k plus 1 factorial?
Mm-hmm.
Can we bring k plus 1 factorial to the other side and prove that this is less than 0?
Yeah, sure. That's algebraically equivalent. You can prove anything that's algebraically equivalent to this. So
Okay.
if you, sure, somehow if this makes life easier for you.
Well, in this case, no, but I think that on the quiz, it was easier for me to show that it was an addition of two things that are greater than 0.
Yeah.
So the whole thing is greater than 0, than to go from the one side to the other.
Yes. Yes. Sure. You can do it. Sure.
I have a question too.
Yes, please.
How did you get from k plus 1 factorial to 2 times k factorial?
I just erased it. Okay, so, all right, so, okay, so what did I have? Somebody help explain this, answer this question. Can somebody who?
It was because of
Yes.
k is greater than 4 or equal to 4, then the 2 will always be less than k plus 1. So the 2 times k factorial will always be less or equal to k plus 1 times k factorial.
Okay, does everyone see this? Why this step, not that step, why this step is justified? This was the question. 2, I have 2 times k factorial. 2 is one of those terms in the product, 2 times k factorial. That 2 is definitely smaller than k plus 1. Why? Because I'm taking all these k's that are bigger than 4. So something bigger than 4 plus 1 is definitely going to be bigger than 2. Therefore, 2 times something is definitely smaller than k plus 1 times that same thing. The same thing being k factorial. Does that make sense to everyone? Any questions about this? Any more remarks, questions, anything? Okay, now I want to do this one, but let's first do a couple of examples with strong induction. So strong induction, somewhat misleading, the name. It tells us that you get to assume more than in our previous version of induction. So the setup is exactly the same as before. Again, where the goal is to prove the proposition that's indexed by n. So you have some P of n, sequence of propositions that you need to prove. Again, the base case is exactly the same as before, but the inductive step is where you get to assume that not only P of k holds, not only P of k. So again, you want to prove that P of k plus 1 is true, given that not only pk is true, but pk and every proposition that came before it, all of these and all of these propositions, let's say I'm starting at 1, all of these propositions are true. Does that make sense? So that seems like it's a genuinely stronger requirement. So not only you get, so in all of these previous examples, in the inductive step, we wanted to prove the implication that P of k implies P of k plus 1. In this version of induction, which is, by the way, equivalent to our previous version of induction. Okay. Okay. You get to assume that not only P of k is true to prove that P of k plus 1 is true, but also that P of 1 is true, P of 2 is true, P of 3 is true. and P of K is true. All of these propositions that came up to K inclusive, all of those are true, and therefore P of K plus 1 follows. Now, this seems like it's a genuinely stronger principle, but both of these principles are equivalent, and yet they're equivalent to a third principle called the well-ordering principle. Okay, they can be shown to be equivalent to one another. Okay, and in fact, if you have a proof by any one of these principles, it's a simple matter of writing a computer program to convert that proof to a proof by another one of those three equivalent principles. Okay, so but if you're proving something as a human being, then it may be easier to apply one of these versions of the same principle to the problem at hand than another. Okay, so let's see. So here, let's, okay, so this is, I'll let you read that. Okay, so let's do this example here. So now we're going to prove something using strong mathematical induction. You know the fundamental theorem of arithmetic, that every number n, integer n greater than 1, can be represented as a product of primes in a unique way. Okay, up to the order of the terms that you're multiplying. So for example, 18 is a number. It's a product of primes. It's 2 times 3 times 3. You can have repeated primes, sometimes written down as 2 times 3 squared. So 2 is a prime. So let's consider 2 to be the first prime, and let's actually start this 2, not to confuse matters. So every integer beginning from 2 and upward can be represented as a product of primes. So 7, is 7 a product of primes? Well, yes, it's just there's one prime in that product. It's 7. So there's one prime, one term. Here you have 3 terms, 1 repeated. Okay, 3 terms, and so on. Okay, so any integer. So our goal is to prove, using induction, that any integer can be represented as a product of primes. Now, you may have proved the uniqueness in part 1 of this course. So it's actually not can only any integer be represented as a product of primes, but if that representation is unique, that's the second part of this theorem, which you may have proven as an exercise on proofs. Okay, proofs by contradiction, maybe you've done in the first part of this course. So there you probably prove something like this. We're not going to bother with uniqueness. But the way you prove uniqueness in this case, and many uniqueness theorems in math, you assume that by way of contradiction, that there are 2 ways of representing that integer as a product of those primes, and you arrive at a contradiction. We're not going to bother with that. What we're going to prove here is by induction that every integer has a representation as a product of primes, and we'll leave it a separate issue that it's a unique, that representation is unique. All right, so the proof is by mathematical induction, strong mathematical induction in this case. Okay, by strong induction. Okay. Okay, so okay, so help me out. So again, it's exactly the same as before. The only difference is that in the inductive step, we get to assume more, which seems like it should be a stronger principle. You get to assume more after all, so it must be more powerful, right? To prove that pk of plus 1 is true, not only do you get to assume that p of k is true, but p of 1 is true, p of 2 is true, p of 3 is true. So what's my p of n? So what am I trying to prove? Just that's p of n. Again, in all of these examples, p of n, but we haven't seen any creative uses of mathematical induction yet, where you have to modify, you have to come up with some clever predicate just to prove something interesting. So p of n is what we're trying to prove. N is a product of primes, is a product of primes. Sense that we just talked about here. 18 is a product of 3 primes here. Okay, now if you'd like to be like super duper clean in writing up the proof, which I'll do on the side, but you wouldn't have to, just so that people see. So what we're saying here that n, what we want to prove, is a product of primes, like maybe, I don't know, k primes, like p1, p2, blah, blah, blah. All these are primes, p of k. And each one of these primes maybe goes into that product with some power, like 3 went in here into 18, like 3 squared. So, like that. Okay, some of these powers may be 0, right? So, for example, I don't know, let's take 60. Okay, that's going to be 2 times 3 times 2 times 5. Okay, so that's a bad example, but anyway, 7 goes with the power of 0. So let me 540. If I go with, let's say, 540 or something. No, that's 6. What should I do? 6. Okay, this is fine, like in anything. So 7 goes with the power of 0 there, let's say. Okay, think of a nicer example. Should have said, like, what should I have said? Right, so do people see what I'm trying to say here, or no?
Can you use the same prime twice?
Yeah, I just said that for 18 here.
Okay.
Is it clear what I'm talking about here? Okay. What is, so here you have 84. So this product here, this is what I'm trying to say. The 2 goes with the power of 2, 1 goes with the power of 5 goes with the power of 0, and 7 goes with the power of 1, right? So some primes may go with the power 0, means this is 1. Primes can go with the power 55. Okay, so 2 to the power 55 and so on. So what we're trying to say that any n can be represented like this. That's what we're proving. Now, for a neat write-up, you'll probably have to write something like this down, but for us, it will just clutter the page. But I will still have this notation on the side for people who want to be super precise, to look at an argument like this precision and don't like muddled thought, right? So I'll keep that just on the side. But the most important thing here is to argue to have like sentences in the natural language in English sentences clear, which is the same thing. All right, so the proof is by strong induction. What's my base case? The base case is the same. Base case, we're starting at 2. It's true for 1 too, but start at 2. What is P of 2?
Two equals.
Yeah, so what is it again?
2 equals to 2.
2 equals 2, exactly. It's a product of primes. So 2 is there's just one prime in the term, like 7 equals 7 here. There's just one term in the product. So 2 is a product of primes. So we're just proving it for the first case, base case. How about the inductive step? What am I proving here? Now, if I were using just the usual induction principle, what would I be proving here?
We would assume that there's some k, arbitrary k, and that P of k is true. And then we're trying to prove the implication that P of k plus 1 is true.
Exactly. Assume that for arbitrary k, pk is true. So what would pk be? Okay, now we'll be doing this by strong induction, but let's for a second, let's humor this idea. So suppose I'm trying to apply simple induction. So I'm assuming that pk is true, and I want to prove that pk of plus 1 is true. Now, the most important piece always in every proof, let's say this in words, not just pk, but let's translate this into English. So what are we saying? Let's just apply the effort to just say it.
K equals some number k equals some product of prime numbers.
Yes. So K is a product of some primes, just like that. So instead of n, I have K. K is a product of primes. And I want to show that from that, somehow it follows that K plus 1 is also a product of primes. So I get to assume that 77 is a product of primes. It's 7 times 11. Okay, 77 is a product of primes. Can I conclude from this that 78 is also a product of primes? How? Why does it follow? It beats me. I don't see it. Maybe somebody else sees it. So I have some number K. Something, if you want to have a concrete one in mind, let's take 77. Why does it follow from this that 78 must be a product of primes? Whence? Where does it come from? That's not obvious. So let's try strong induction. So if we're doing this proof by strong induction, we get to assume that PK is true, P1 is true, P1 is, P2 was started at 2. P2 is true,
For your example with the 77, are we assuming that everything before that already?
Now we're going to assume that because we're going to try a proof by strong induction. In the case of 70, if I wanted to prove the 78 was a product of primes, somehow I couldn't deduce that from the single assumption that 77 was the product of primes.
Did you say something about it being divisible by 2, which is a prime, and then the number obviously smaller than 78, so it also has to be a prime.
Yes, so our proof, we'll just write that idea, we'll just write it out cleanly. Yes, so you can reduce, so you get to assume, but the point is, so we get to assume that everything before 78 is a product of primes. Well, I could have used a different example that's not clearly, let's say if I said, well, I can deduce that, let's assume that I know that 78 is a product of primes. And I now conclude that 79 is a product of primes just from that. How exactly? This should work for any K. So now 79 is not even, but the idea is,
right. Either you can create it from 2 before, which were primes, or it has to just be a prime.
How exactly from 2 before?
Well, just like if it's possible to create the number by multiplying it by other numbers, and then we know that those other numbers would have to be primes because we've already assumed that.
Product of primes because they will be smaller. That's what we'll argue in a minute. If I'm understanding you, I think that's what you. Okay. Let me argue this, and then you tell me if that's roughly what you had in mind. Yes. Okay. So let's assume this. So let's do this by strong induction. So P2 is true, P3 is true, P4, and every one of these. So is it clear what I'm assuming? That each number up to P of K, each number starting from 2 and up to K. This K may be not just 78, like any number, like 78 gazillion. Anything before then can be decomposed into a product of primes and be represented as a product of primes. Now, why does it follow that K plus 1 is also a product of primes? So let's argue this. And I think I'll argue what you've just suggested. Just let's write it down. So, well, actually, let's look at 2 cases. So, okay, so let's write this down. We want to show, so we get to assume this. For an arbitrary K, this is what we get to assume. Now, want to conclude somehow that from this assumption that P of K plus 1 holds. In other words, K plus 1 is a product of primes. So why? This is what we're justifying. Just writing down this in words. It's a product of primes. Just like this. This K plus 1. Okay. So I have 2 cases. Consider 2 cases. If K plus 1 happens to be prime, like I had the case like 76 and okay, so 30 and 31. Okay, so I know 30 may be decomposed into a product of primes, but I'm not even using it. 31, K plus 1. If it's prime, then it's already a product of primes, just like this 7 here. Okay, if k, so case one, if k plus 1 it happens to be prime, I really have two cases, really. K plus 1 is prime and k plus 1 is not prime. There's no other. That was also okay. So that's roughly the idea that was suggested. So let's just write it out. Okay. So yeah, that's true. That's a good idea. So okay. So k plus 1. Now I want to prove that k plus 1 is going to be a product of primes. If k plus 1 is not prime, if it's prime, then it's clear. It's true. When k plus 1 is prime, Else, just by definition of what it means for this to not be prime, or we can follow yours too, but let's just go with this. K plus 1 is not prime. K plus 1 is not prime. This means that it's a product of two smaller integers. This is not prime means by definition that it's divisible by some smaller integer than k plus 1. So then means that k plus 1 is, just by definition, a times b, where a and b, well, they're greater than 1, both, okay? Both a and b, and they're smaller than k plus 1. It's just by definition of what it means for a number to be not prime, right? It's divisible by something smaller than itself. It's the definition of non-primeness. But by the inductive hypothesis, A is a product of primes, and B is also a product of primes. So A times B is also, okay, also a product of primes. Okay, for people who like to see this written out, okay, you can write it if you'd like. It's not necessary here, but you would write something like A is, well, it's P1, blah, 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 P of L, like A1, A sub L. It's a product of primes. B is a product of, let's call them Q's, Q1 to some power, blah, 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 Q, M. Okay, it's a product of primes, each one. So therefore, A times B has to be product of these primes with those powers, right? Okay, so you have all these primes. Some of these may be repeated, okay, but still, it's a product of primes. Okay, so here is the decomposition of A times B. And it follows from the inductive hypothesis. Where did it follow from the inductive hypothesis? Because we assumed all of these. A and B is one of these. It's either one of these guys somewhere. A and B are smaller numbers than k plus 1. So for those we can decompose into products of primes, and therefore A times B is a product of primes. Makes sense, right? Okay, that's a proof by strong induction. This is a good example to do. We'll do that next. But okay, so I want to talk a little bit. Okay, so I want to talk a little bit about, well, what's to come, and then one more example. Okay, now we talked about mathematical induction. We'll do more examples for practice, but we've covered the basics for sure. Okay, so now we'll see that mathematical induction is very closely tied to the idea of recursion. Okay. You have written recursive programs before. In an introductory programming class, you will probably, one of the first assignments is to write something like, I don't know, n factorial recursively or something like that. You've written stuff like this. So you've written a small recursive program, right? So we'll talk about objects defined recursively. What does that mean? You define an object in terms of itself. Okay, you'll say that sounds like circular reasoning, but it really is not. It's defined as a small, in terms of a smaller version of itself. Okay, just for example, I'll talk about n factorial as an example in a minute. So n factorial how is it defined? It's defined as n times a factorial of a smaller version of n. So I don't know what factorial is, but if I knew what the smaller version for n factorial was, what a factorial meant for n minus 1, then I can compute the factorial for n by taking n and multiplying it by that, what I'm assuming to know, what I'm assuming is known. Okay, this may not make complete sense, but we'll see examples in a minute. Here's an example of a recursively. So we'll define some structures recursively now, and then we'll try to find out certain truths about those structures. And because they will be recursively defined, we will see that it's easy to use mathematical induction to prove those things about those recursively defined structures. Okay, so now all this is verbiage for now. So let's see a couple of examples of recursively defined structures. First of all, let's start with a simple example, like a sequence like this. So a sequence, what is a sequence? In calculus, you probably wrote sequences down like this. Okay, so this, by this, you understood what a bunch of numbers. For example, 2 to the n is a sequence, 2 to the 0, 2 to the 1, 2 to the 2. When you talked about limits, I think that's the way you wrote them down. Okay, 2 to the third, and so on. Okay, that's how you wrote down sequences before. It's understood this sequence is a function. It's a mapping, right? What does it map to what? Why do I say that a sequence is a mapping? So help me out. In what sense exactly? What do I mean by that? Somebody help me out. So we know what a function is. It's a mapping. How is a sequence a mapping? What's mapped to what by a sequence? Take a sequence.
N is mapped to whatever the terms of the sequence are.
Yeah, exactly. So you take, so here's your domain is 0, 1, 2, 3, blah, 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 and blah, blah, blah. 0 is mapped to a sub 0, which is in this case just 1.1 to the, or 2 to the 0th power. That's just 1. 1 is mapped to this a1, which is 1.1 to the power of 1. A sub 2 is mapped to a 1.1 squared, and so on. So what you have is a mapping from, so the sequence is a function. It's a mapping from the natural numbers like 0, 1, 2, 3, 4, to the real numbers. In that sense, it's a function. It's nothing but a function, right? It's just a mapping. The claim is that we can define, so it is a function, that we can define this function recursively. Okay, what do we mean by recursive definition of a function? Now give a definition here in a second. Well, notice how it mirrors the structure of inductive proofs. Notice that we're not proving anything now. We're defining something. There's no proof involved, but the structure of it will be as follows. To define this sequence recursively, we'll start by what we call the base case of the definition, And I'll ask you in a minute, like in your recursive programs, like when you wrote a computer program to compute n factorial, what did you call the base case there? Did you refer to anything as a base case there in those recursive programs?
N is 1.
Yeah. Okay. So base case here, you take, let's start from 0, or you can start at 1. So a sub 0 is, let's go with this one, is 1. That's my definition. So I'm defining the first term of the sequence. And then I have not an inductive step, but a recursive step of the definition, which says that any nth term of the sequence can be defined in terms of the previous term of the sequence. In particular, for this sequence that I'm defining, every term is going to be twice the previous term. This defines a sequence just as this mapping, the orange mapping defines this same sequence. Okay, we did 2s here. Okay. Defines this sequence, a sub n, defines this sequence. Well, you can ask me, like, what is like a to the 5th? Well, I'll tell you, I don't know what a to the 5th is. You'll say, well, I know, and according to this mapping definition, I can tell you exactly what a to the 5th is. I take 2, take it to the 5th power, it's going to be 32. Exactly the answer. If you ask me, I'll say, well, I don't immediately know what a to the a-fifth is. A-fifth is. I don't know, but I can compute it for you because I know what a0 is. It's 1. And I know that a1 is going to be 1 times 2 according to the recursive step. So that's going to be 2. A2, I don't know what it is yet, but I know that the previous term was 2. So it's going to be 2 times 2 according to the recursive step of the definition. So now I know that a sub 2 has got to be 4. Then a sub 3, I don't know what it is yet, but according to the recursive step, it's 2 times the previous term. And I've already computed the previous term. That was 4. So that's going to be 8. A sub 4, I don't know, I'll say, but can compute it for you. It's going to be 2 times 8 because that's the way that the sequence is defined, and that's 16. A fifth, well, I don't know what it is, but it's 2 times 16, and that works out to 32. And now I'll give you the answer. I'll return the answer. I'll say it's 32. And you'll go, oh, okay, that's exactly what I thought. You say a fifth, I knew it was 32. Because according to my definition here, orange definition, just plugged in the n, and it gave me 32. So either way you want to define it, you still define the same object, whether recursively or the way you did in calculus. Now, it turns out that certain recursively defined sets, certain sets to certain objects that occur frequently in either mathematics or in applications, for example, in computer science applications, for example, trees. We'll talk about trees a little bit, the special kinds of graphs. Those can be recursively defined. And with structures that are recursively defined, it's easy to prove certain results using mathematical induction. And we'll see examples of this coming next, like next time. Let's give one quick example of a recursively defined function. So 2 to the n was 1. So here's 1. Here's a function. That's recursively defined. How? Basis step tells me that at 0, this function is going to be 3. I don't know what this function is going to be at f of 3. I don't know, but I can compute it because f itself, the function, I wasn't given a graph of it or anything like that in calculus. There's no graph, but its values are recursively defined. So I know that according to this recursive step, f of 1 is going to be 2 times f of 0 plus 3. So that works out to 2 times 3 plus 3. I think that's 9. And f of 2, I don't know what it is, but it works out to be 2 times 9 plus 3. So that works out to be to 21. And so on. So you get the idea, right? Is that right? F of 3, don't know what it is, but it's going to be 21 plus 3. So that's 45, and so on. You get the idea. You can compute f of like 55th, and so on. So that's a recursively defined function. We'll return to this idea next time, and we'll define sets recursively. We'll define other objects. We'll talk about trees, define them recursively, and then prove some facts about them. Then we'll use induction. Okay, so far just simply notice that this recursive definition is somehow, and it conjures up the imagery that you may have in mind that was deposited there as you carried out your inductive proofs. So now you have some idea about induction, and the recursive definitions are closely related to them. Now, back to induction. Okay, so it's clear, right, how induction works. So you can't possibly be fooled if someone gives you an inductive proof of something, and it seems like the conclusion is absurd. Okay, so I want to prove that all the horses are of the same color, and your job is to catch me in a lie. Okay. So first of all, if I want to prove a statement like that, right? So far, all the examples that we had involved some n somewhere. Okay, and induction can be used much more broadly. If you read the textbook, there are a couple of examples there of pie fights and all that, the funny examples. We had more examples that we're now not going to cover with Bill Gates and so on and so forth. But those we're proving propositions indexed by n in inductive proofs. To prove something like that all horses are of the same color, there's no n there. For me to be able to apply induction, I need to work n into, I need propositions. Okay, so all the horses, an infinite number of all the horses that I see, they will be of the same color. That's what I need to prove. How do I prove it? Well, I translate this into a proposition then I can prove using induction. And the proposition is this. This is the theorem that we want to prove. In any set of n horses, you see some number of horses, they're of the same color. Okay, so this is what we want to prove. And the proof is going to be by induction. Is by induction. Okay. Let Pn, I'm following the template just as before. Pn be the proposition like, okay, this proposition. Any n horses are of the same color. That's my Pn. Same color. Okay. Okay. Now I have my proposition. It's indexed by n. So I'm going to start with the base case. P of 1 is true because you see one horse. Look at one horse when k equals 1. Okay. And it's of some color. So all the horses in that set of one horse sets, any set of one horses that you take, all the horses there in that set will be of the same color. There's only one horse. Oh, it has some color. Okay. So all the horses there are of the same color. Checks out. Base case. Easy. The inductive step. Inductive step. What do I need to prove? So help me out. So we're just following the template. So everybody knows inductive proofs by now. We've done several examples. We'll even do more next time. So what should I prove? Must prove that P of k implies P of k plus 1, right? That's just following the template. I looked at my cheat sheet. That's the next step. It says is what you should do. We prove the implication. So assume, first of all, I should be asking, what now in words, what is pk? What is pk plus 1? So assume pk is true. So what is pk? Aside. So aside. P of k is P of k plus 1 is. So what is it that I'm proving? Just following the template. So what is P of k? I'm assuming P of k is true.
P of k is some number. For some number k horses are all of the same color.
Any k horses are of the same color. Okay, that's P of k. So let's draw some horses. Instead of drawing, I'll just put a letter H there. H1, H of k are of the same color. Let's put more horses. H1, H2, ... H of k plus 1. I have k plus 1 horses. Okay, so these guys, any k horses, according to my pk, any k horses, like these k horses, are the same color. Suppose yellow horses or something. These guys, there are k of them, so k of them. These guys, because there are k of them, must be of the same color. Okay, some same color. Therefore, so what we have, notice what we have. So color of H1 is the same as color of, let's say, HK, right? And could have taken any other horse in between there at the intersection, at this intersection here. And color HK plus 1 is the same as color HK by the inductive hypothesis, any set of H colors. So color H of 1 equals color, same color of HK plus 1 So all k plus 1 horses are of the same color. Okay, so I've just proven that all k plus 1 horses are of the same color. Okay, so I had an inductive hypothesis. All k horses, any set of k horses, they're of the same color. I've proven that if that's the case, then any set of k plus 1 horses will have the same color, k plus 1, k. P of k, that was that. P of k plus 1 was this proposition. Okay, so here's a proof. Here's a proof why every set of any set of k plus 1 horses you take, they have to be of the same color if you get to assume that any k horses are of the same color. And here's the justification. Take any set of k plus 1 horses. Well, if any subset of k horses in that set of k plus 1 horses are of the same color, all right, take this subset here. Same color, then take this subset here. Same color. Well, every horse then has to be the same color because of transitivity, because H1 is the same color as this guy, anyone here, and anyone here is the same color as this guy here. So this guy and everyone in here are of the same color. So all k plus 1 horses are of the same color. So, okay, so I've just proven the inductive step. Then I have one more thing to say. So we've just shown the base case. We've just proven the inductive step for this proposition. Therefore, by the principle of mathematical induction, all horses are of the same color. P of n is true for any n. No matter how many horses you take, all of those guys will be of the same color. Okay, proof is complete. I'll write down my QED and I'll go home. That's it. Proof is complete. And you'll say, oh, well, wait a second. It's clearly absurd. I mean, I've seen pink horses and purple horses out there. There's no way. How come you're telling me they're of the same color? How is this? Where am I lying? Am I lying?